How about now? I guess we can start. Welcome back, everybody. Any questions folks would like to discuss on the homework or other questions, upcoming exam before we start today?
Are we gonna have a review on?
Yes, we will. So our plan for very next week is on Thursday, we're going to finish up what we do not cover on 11.2 to finish out that section. And on Wednesday, we'll be reviewing for the exam. And the notes for the exam still haven't been updated, or no, they have been. But the sample exam 2 problems haven't been updated to have the course book problems. Once that's reflected, I'll say updated with a date. The extra material is there's an exam 2 that was given in spring that folks could use as a benchmark of what a real exam would look like. At the very bottom, you'll see the solutions. These are typed out by hand, so it's easy to make a typo, easy to make just a flat out mistake. So if something looks off, just let me know and I can come back and take a look and correct it. Other questions about the exam? Okay, one thing to mention is we did, in fact, delete 11.3 from the list on the sections for exam 2, which means 11.3 is now here on exam 3, and 11.10 is kind of in question. But that's just the way it goes being a day behind. We don't necessarily want to rush because 11.11 is kind of considered fluff. So if we have to give up a section, that one's gonna have to take the fall for us. But any questions then before we start our work for today?
So,
Yeah.
on exam 3, you said that we're gonna just go over all of chapter 11, right?
For exam 3, it's primarily chapter 11,
Okay.
except for 11.1 and 11.2.
So when it says on the final exam that
Yeah.
it's gonna focus on those 5 sections? Like,
Yes.
How, like, what does emphasis mean?
That's a good question. What I'm going to do is just look at all of the sections, and I'll take the sections that we have had an exam on. And these particular sections, they may be worth altogether on the final exam, maybe about 20% maximum.
Oh,
But if we look at the previous sections, I can't actually ask a question on every single section we covered because that's already a pretty long exam. So it might be kind of spotty in the exam 1 questions that are actually on the final. But the final would have a question, at least one, from each one of these sections.
oh,
So that's what we mean by a slight emphasis. But other questions about that? Okay, so we are back to 11.1. 11.1, we've done a couple things. We defined what we have meant by a sequence, and we've also looked at determining what the limit of a sequence should be, essentially purely by analyzing its graph, which is a tough thing to do and very misleading. But we mentioned there's also very powerful limit laws that we can leverage to help us to solve some of these sequences. So let's do a couple more of those problems as a warm-up, and then we'll go from there. Any questions before we start then? Okay, so the typical instructions for a section like this, really much of the entirety of chapter 11, would say something along the lines of determine if the following sequences, and later on it may say series, converges or diverges. And there's many different ways we could write these sequences. For example, we could be looking at things along these lines. How about the sequence that goes 4, -1, 1/4, -1/16, +1/64. All sequences are infinite, so we'll put ... to say this pattern that we have here will continue forever. In some sense, this is not fair because there's infinitely many different patterns that could continue from here, but we'll take the most obvious and likely pattern that we see to be the one that's meant by this sequence. So we want to determine if this converges or diverges. Well, what would you folks say about it just by looking at it, purely by inspection? It should converge to 0, right? I mean, this seems like the case. We can visualize if we plot all these things, the values are getting smaller and smaller and smaller, and they're tending towards 0. So we could say this converges to 0. And that could be fine for a lot of sequences written like this. But again, we have to be very careful because occasionally these things are very unpredictable. They don't always behave like we'd like. So let's do a second solution to this. Let's determine if we really believe it converges to 0 by first find a formula for the nth term a sub n. That could be a bit of a skill in and of itself. Take a random pattern and find a formula that dictates what we should have. So in order to do that, really we're going to just essentially do trial and error until we build the correct formula. And the first feature I see with this sequence is it's alternating in signs, from positive to negative and so on. So when we build the nth term, a sub n, we could say, first let's add this component, -1 to say a power n. If we do that, then we have one feature of the sequence. This is going to alternate between positive and negative. N is going to start at 1, so we have a problem, right? If we say a sub 1 in this formula, that'd be -1 to the power of 1, which is negative. But we need to start at positive 4 in particular. What should we do then? Yeah, if we multiply this whole thing by -1, that'd be effectively increasing the power by 1. We'd have -1 to the power of n plus 1. If that's the case, our new a sub 1, we'd plug a 1 here, it'd be -1 squared, which would be a positive 1. Again, we're looking for a positive 4, but at least we have a pattern emerging where now a sub 2, if we put 2 here, we'd be looking at -1 cubed, which is now -1, and it looks like we have the right alternating pattern from positive to negative and so on. Now we have to capture the 4, the 1 at the 1/4, and so on. So we'll keep on building on our formula until we get just the right thing. But any questions to that step? Okay, so there is something going on with the 4s. So we have 4 to the power 1, looks like 4 to the power 0, 4 to the power -1, and so on. So we should put 4 to some power, but again, the key is getting the right power, just much like we had to adjust n to n plus 1. So we could start, say, 4 to the power of n, and just see what happens with that. But if we do that, we have to check what would emerge in our terms. Say if we look at a sub 1, we'd be squaring -1 for positive, so that's good, and that didn't change. We would get a 4, and hey, a sub 1 matches with what we want. Is this good though? Should we check further? I mean, we have the right first term, but there is infinitely many other terms here. So let's check a sub 2. In a sub 2, we'd be cubing -1, so it's negative. Here we'd be squaring 4, so it's 16. And that's a problem, right? A sub 2 should have came out to -1, which means we still have to make an adjustment. The power of n was not quite right. So we go back to the chopping block and change something up here. Anyone see what a change could happen, or what good change we could make to that? Let's make -n. Really, we're just kind of messing around until we get to something we need, right? I like -n because 1/64 is really 4 to the power of -4, so we should have really a negative exponent to make this work out. So let's check out what 4 to the power of -n would come out as. Again, we're not trying to hit it in one shot, we're just edging our way to the correct answer until we nail it. So now a sub 1, this is once again positive, 4 to the power of -1 is 1/4. So we have positive, but notice we're off by a factor of 4. That's okay, well, certain factors of 4. We just need to do something else inside here. So if I got 1/4, but we're expecting 4, what should we add to the -n to get right to our target? It's kind of like a game of hot and cold, right? It's getting warmer, but we need to make an adjustment. Should we say add 1, 2, or 5, or subtract? How do folks feel?
Add 2.
Let's add 2. I like that because if we multiply by, say, 4 squared, that's what we're missing right here, we would have gotten a 4, which is what we're expecting. So adding 2, let's check if this really works. A sub 1, we'd be squaring -1. We've done that dozens of times now, it feels like. This would be 4 to the power of -1 plus 2, which is 4 to the power 1, which comes out as 4. So a sub 1 is resolved. Let's just check a couple more until we feel like we have substantial evidence that we have the right thing. In a sub 2, we'd be cubing negative 1, so it's negative. This would be 4 to the power of 0, but 4 to the power of 0 is a 1, so we get negative 1. And it looks like we're on target. If we get 2 terms, I mean, we still might be off, right? But let's keep on checking. A sub 3, that'd be plugging in 3 here, so this would be to the power of 4, so positive. 3 here would be 4 to the power 1, but that would be, negative 3 there, plus 2, would be 4 to the power of negative 1, which is the 4th that we're looking for. That seems reasonable as we go to A4. This would be 4 to the power of negative 2, so 1/16, and we'd also have negative. So I'd say at this stage, we found the nth term. Again, by the instructions, we could have just said converges to 0 and be done, but if the instructions, and some of them in the homework say, find a formula for the nth term, we would have to do all of those kinds of steps. But getting to the exact answer in one shot is kind of tricky unless you've done a bunch. I would just do something like this. Get some scratch paper, start playing around until we get warmer and hit the exact sequence. But questions so far, building the nth term? Okay, so now if we have the nth term, another thing we can check here, if that nth term is reasonable, then we should be able to take the limit of that sequence and see that it converges to 0. So let's check that out as well. We have the limit as n goes to infinity of a sub n is now the limit as n goes to infinity of negative 1 to the power of n plus 1 times 4 to the power of negative n plus 2. So let's do that limit while we're at it. We're doing loads of things at once on this problem. So next, if I were to work out this limit, we could leave, say, the negative 1 to n plus 1 alone, call this the limit as n goes to infinity of negative 1 to the n plus 1. And this is kind of awkward to deal with. What I'd probably want to do with it is convert it down to the denominator using exponent laws. If we place base 4 in the denominator, then we'd have to negate the exponent. It'd become positive n and minus 2. So that would be the statement so far. Any questions to that step? What I like about the numerator is it's bounded between negative 1 and positive 1. So it always has a size of 1 in absolute value. However, the denominator is growing without bound. The exponential function, 4 to the power of n minus 2, is just going to get larger and larger as n increases. So we can say that this is going to be 0 in the limit. Does that make sense to folks with that rationale for the limit? Okay, so if we have something constant or bounded, and something growing without bound in the denominator, overall the whole limit converts to 0, and we can say the sequence, now we're really, really sure, definitely converges to 0. So that's a review of what we were looking at in 11.1 last time. Any questions so far about that limit? Okay, so there's many different ways to write the sequences. In some sense, this is kind of the worst way to do it, but it's still valuable to see them this way, know how to convert to a formula, because if we want to find the limit of a sequence, it's nice to have a formula for the nth term. That way, all of the limit laws that we have can be leveraged to help us out. Let's look at a couple more, just for the sake of practice. Another important limit law for sequences that we haven't quite looked at yet looks about like this. This one we call a bona fide theorem, and I think this is theorem number 9. The theorem says to consider or let R be a real number. Then, we have a few cases that we'd like to look at for limits involving this R as a base. We can say if R is equal to positive 1, then the limit as n goes to infinity of R to the power of n, and this is the limit we're going to take in every case. Let's call this case 1. This would be the same as the limit as n goes to infinity. Well, r is 1 in our simple case, r to the power of n is always 1, and the limit of a constant would be 1 itself. So that's what would happen if r is 1. Any questions with that first case? Another case that we can look at, let's call this case 2, says if the absolute value of r is, running out of space, if the absolute value of r is less than 1, then the limit as n goes to infinity of r to the n in this case would be 0. So that sequence, a sub n is equal to r to the power of n, where r is less than 1 absolute value, would always have a 0 in the limit. Folks believe that limit statement? Does it seem plausible? Okay, one way to kind of see why that ought to be the case is if a sub n is equal to, say, maybe 0.75 to the power of n, then the limit as n goes to infinity of 0.75 to the power of n, well, the terms in this sequence would start as 0.75 when n is 1. When n is 2, we take 0.75 times 0.75. In other words, we're taking 75% of 75%, so it's shrunk. When n is 3, we'd be taking 75% of the previous result, so it's smaller still. And in the end, this whole thing would converge to 0 in the limit. So we could call that a case 2, kind of the nicer case. Case 1 is just an oddball case where the entire sequence is constant and it has a limit 1 by default. Any questions with that second portion? Okay, then the third portion says if the absolute value of, let's say, maybe this way, how about if r is less than or equal to -1, or r is bigger than +1, so we've excluded the case that r is equal to 1, we've exceeded that. R is less than or equal to -1 means we've left this case, so we're looking at every other situation other than case 1 and 2. In these cases, we can say then the limit as n goes to infinity of r to the power of n does not exist. So in other words, really the only way that a limit of this type is going to exist is if r is 1 itself or less than 1 in absolute value. But if r is -1, then the terms of the sequence would look essentially like this. We'd be oscillating between +1 and -1 forever when r is -1. So the terms would look like that. But for the limit to actually exist, the terms have to approach each other. So in this case, when r is -1, it does not exist. And if r was something like, say, 1.5, the values would just get larger and larger and larger and look something like that. So those are the three great cases, which are going to give us even more limits that we can compute. And in fact, this case right here is going to be used later on in section 11.2 in the geometric series test. But questions so far about that theorem? Okay, so let's look at ways we can calculate limits using that. So with the same instructions, we're going to determine the convergence or divergence of a new sequence. This time the sequence is going to be indicated in a slightly less annoying way. The nth term is given as a sub n equals 3 to the power of n divided by 1 plus 7 to the power n. So we want to imagine what all the terms of that would look like. If it's converging, then the height of those terms plotted on an xy plane should be convergent to constant height. If it's diverging, it could be oscillating forever, like in this case, or heading towards positive infinity or heading towards negative infinity. But in either case, we're going to use limit laws and our fancy new theorem to find the limit as n goes to infinity of this sequence. 3 to the n, 1 plus 7 to the power of n. And the trick is we have to leverage these kind of statements while using the limit laws for sequences 1 through 7. So, any questions then before we start? Okay, the trick to this one is very similar to the trick that we used on rational functions, where we mentioned that you could take a shortcut. In this case, though, we would want to write out the steps and first focus on the exponential function, the denominator, that has the largest base. If I take the 7 to the power of n, divide every single term in the numerator denominator by that quantity, this is what we would get by exponent laws. It would turn into the limit as n goes to infinity of divide 3 to the n by 7 to the power of n, and you can consolidate this to 3/7 to the power of n. So we have something much like in case 2, some r, which is 3/7, less than 1 in absolute value, which we're raising to the power of n. If this was all we were looking at, this would converge to 0 immediately. So we have to be careful because the denominator, if it converges to 0, we'd have an indeterminate form. So we continue to divide. Take 1, divide by 7, that could be raised to the power of n, and divide 7 to the power of n by itself will give us that. So that's what the limit would convert to. Any questions to that step? Okay, so this is just the right thing that we needed. We're going to use theorem 9 twice, but we're also going to say the limit of a quotient is the quotient of the limits. In other words, we take the limit of this, which would become 0 by theorem 9, because we have a case where the value r is less than 1 in absolute value. Down below, this would convert to 0 as well in the limit, and we get plus 1. That plus 1 is really helpful because now it's not in an indeterminate form. It's 0 divided by 1, which is 0, so we can say that an, defined to be 3 to the power of n, 1 plus 7 to the power of n, converges, I'll just write CONV when I run out of space, to 0. So that's how to resolve those kinds of limits. Any questions with that one? Yeah.
Is the n on 7 or is it on 1 and 7?
It'd be the 1 and a 7. And you could, in fact, just say write it this way as well if you prefer, 1 over 7 to the power of n, because raising 1 to the power of n does not affect it. And you would get the same value. Here you could say, however, that you have something constant divided by something growing without bounds, so still a limit 0. Other questions about that one? Let's try maybe a trickier one next. Let's take the limit as n goes to infinity, and this one just has strange constants this time. It's going to be, how about a e to the power of n plus 7 divided by, let's make this be, how about 2 to the power of n, why not? So that's the limit we'd like to do this time. So it's kind of similar as before, but now dealing with 2 to the power of n, we have a different kind of situation, but still do the same sort of thing. Take the entire denominator, there's no choice this time, divide it into the full numerator, and we'll just see what we get. So this converts to the limit as n goes to infinity of e to the power of n divided by 2 to the power of n is altogether, I'll use brackets, e divided by 2 to the power of n plus 7 divided by 2 to the power of n. So after we divide, that's what we would get. And much like we said with 1 over 7 to the power of n, this portion here would converge towards 0. But we have to look at e divided by 2 to the power of n. What would folks say would happen to that in the limit? It would go to infinity, correct. And the reason for that is e is about 2.7 and some change. So if we take e divided by 2, we're really down in this situation. The base r has exceeded 1, so the limit does not exist. And in this particular case, it would tend towards infinity. If you have something larger than 1, this portion is going towards infinity, while this portion is going towards 0. So we would write infinity like that for the whole value. And simply because for our rationale, e divided by 2 is larger than 1. So that quantity to the power of n will just grow without bound. Any questions about that so far? This is a second problem. I feel like we need a border. How about that? I guess another question would be, would the sequence e to the n plus 7 divided by 2 to the power of n, does it converge or diverge then by this work? Yeah, if we get infinity, really the limit did not exist. We've just indicated a special way existence failed, so it still diverges. We'll say this time it diverges to infinity. Essentially, the only time we can assert convergence is if we produce an actual bona fide real number, whereas infinity is just a symbol. It's telling us where the sequence is trending towards, but not an actual number it settles on. Any questions with that set of problems so far? Okay, so those are the main problems to look at. Maybe we'll look at just a couple more, maybe one more, just for the sake of looking at other tricky problems we could get into in the homework. Then we'll convert to section 11.2, where our job is not to finish it entirely, but to get a feel for it and finish it off when we come back on Monday. So for the very next one, let's take a look at, there's so many good ones. How about, with the same instructions, a sub n is going to be equal to the nth root of n. So that's a pretty wild sequence. If n is 1, we'd be taking the first root of 1. Well, the first root is just the power of 1 itself. If n is 2, we'd be taking the square root of 2. If n is 3, we'd be taking the cube root of 3. And the question is, does this grow, or does it settle towards a number, possibly 0 or something more exotic? Any predictions on convergence, divergence of that thing?
Always go towards one.
Yeah, I believe so. I believe this would converge exactly towards 1. The work is actually showing it though, right? One approach would be to write down, say, 10 terms of the sequence and see if there's a pattern there. But again, that can be very, very tricky with a lot of problems. 11.2, we'll see just a case where our prediction is probably, the most natural prediction is not correct. But if we can work out by using limit laws how the process goes, we'll have a lot more confidence. So limits of discrete points, but this limit as x goes to infinity of f of x is the limit as x goes to infinity of the natural log of x divided by x. And things we know about the natural logarithm of x is that its graph looks about like that, where it intercepts 1, it has height 0, and it grows without bound. Similarly, as x tends towards infinity, this x must tend towards infinity. That's a bit of a tautology. So we have an indeterminate form of type infinity over infinity, which means we can use L'Hopital's rule to settle that limit. So the next step is, this becomes, by L'Hopital's, the limit as x tends towards infinity of the derivative of the top is 1 over x. Derivative of x in the denominator would just be 1. So we have to do that last limit. Keep saying last limit. I think this is the last one though. The denominator of 1 has no influence. Really everything is settled right here. As x tends towards infinity, 1 over x tends towards 0. So the entire limit is 0 itself. But that means by another theorem, theorem 3, the limit as n tends towards infinity of the discrete version of this function, natural log n divided by n, must also be 0. Essentially, the function f of x equals natural log x divided by x is like a guideline, and this sequence is just discrete points along that line. So if this limit comes out to 0, the limit of the sequence is forced to, and that's the entire content of theorem 3. Then we go backwards and recall we're trying to solve this as the limit. We carried a sequence of steps by using laws of exponent laws, and now we have that this whole thing comes out to 0, and e to the power of 0 is finally a 1 in the problem. So we've settled it, and don't forget, we have to say at some point on all the problems whether it converges or diverges. And this one converges because we settled on a constant height of 1. What questions with that problem? Kind of fun? A little bit? Awesome. Well, how do folks feel about sequences then? Any others folks would like to discuss before we go off to a series? Yeah, question?
I don't know if this is a fair move, but can you cancel e with the ln before you do all that? And then cancel the
Right here?
over one?
Right here.
Yeah, cancel out the
Oh, I gotcha.
one, and
The-
then have the 1 times 1 over the n, and then divide out the n, so you just get 1.
Unfortunately, this would block us, sadly. The cancellation could only happen if there's a coefficient of exactly 1 on the natural log. That's a really good comment because I think in 9.3 or 9.5, there's some differential equations where you get an integrating factor. I think that's 9.5. And something like this is going to come up. You'll get e to the power of, say, 2 natural log of absolute value of x. So this is in section 9.5. So this is very tricky because there's no cancellation between e and the natural log as it stands. We have to use the power. Here, the coefficient 2 becomes an exponent on x. It'd really be e to the natural log of x squared, where we can drop the absolute value suddenly because x squared is never negative. And then at that stage, you could cancel this way to get x squared. So I think that does, if I recall right, happen somewhere in the homework, but it's been a really long time. Other questions about that?
Not about that, but I do have a question. So,
Sure.
like, when we were doing the points and you gave us like a vector of numbers, I guess.
Oh, that sequence with the curved race?
What would one look like if it diverges?
Oh, what would the sequence of points look like?
Yeah.
There's a lot of different situations, so let's write down a couple of them. So one divergent case could look about like this. Let's suppose we have a height of 1, a height of -1 here, and we could forever just oscillate between those 2 points. So we could have something that looks like this, and this would diverge.
Oh, okay.
Divergence here is purely because the points never settle towards any constant height. Another case could be something like this. You could have points that are going, I'm going to have a really kind of messed up scale this time. Maybe they start doing this. After a while, something happens, and the heights of the points just increase without bound. In this case, I would say the sequence is diverging, but we can be a little bit more explicit on how it's diverging. This time it's diverging to infinity. Whereas this case, it just flat out diverges. It's not approaching anything, it's not trending towards any specific direction. It's just a plain divergent case. Other questions about that?
So if you had like points like 1, -1, 1, -1, 1,
Mhm.
is that, would you have, like, if we had to solve for the equation, what would the equation look like?
So the sequence for this one looks like you said, 1, -1, 1, -1, and then repeating forever. But that means the nth term ought to be, because of the oscillation, we need -1 to a power. But if we check our terms, putting in 1 here starts us off at negative, not positive. So there's 2 routes. You can either go -1 or +1. I usually go +1, it just feels better somehow. So that would be the nth term of that particular sequence. So if you have something like this,
Okay, I see.
yeah, then it's always just bouncing between these 2 heights. If we want it to force it to be convergent, you could throw in something like maybe 2 to the n. Then we're cutting the heights in half at every single step, for example. Other questions about those 2 sequences? Okay, any other questions folks would like to discuss in 11.1? Okay, let's go to 11.2. So in 11.2, we're finally going to discuss series, and series is going to be a big topic in the entire chapter 11, but series are defined in terms of sequences, so that's the purpose of 11.1. No matter how deep we get into the study of series, we're still dealing with sequences always. So we're going to start with the definition and maybe do something a little bit weird. We're going to plot a series using Microsoft Excel, and I think this is the only time I would ever load Excel in a math class. But while that's trying to load because this computer is slow, let's throw up some definitions. First, this is section 11.2 on series. Series are defined in a complicated way because they are defined in terms of a sequence to start. So that's where we're going to begin in our definition. We say, let a sub n, as n goes from 1 to infinity, for emphasis, that's just the same as writing a sub 1, a sub 2, a sub 3, so on, with infinitely many terms, be any sequence. Okay, so that's going to be the base of our definition of series. So if you give me any sequence, whether my sequence converges or diverges, is totally fine. We can have a new notion of an associated sequence. We'll say, then, the associated sequence of partial sums is defined or denoted first by this sequence with lowercase s subscript n, as n goes from 1 to infinity as well. So s is telling us the sequence of partial sums, really referring to the sums. And the way this is defined by, that's right, it is defined by, we take S1, the very first term in the sequence of partial sums, and we set it to A1. Then we go off to S2. By sequence of partial sums, we mean now S2 should sum the first two terms of the sequence here. So it should be A1 plus A2. Similarly, A sub 3 is A1 plus A2 plus A3. And there's infinitely many terms still in the associated sequence of partial sums. So we can go so on and say S sub n is A1 plus A2 plus A3 all the way up to A sub n. And if you don't prefer the expanded notation, you could just as well write summation as I goes from 1 to n ai, or just leave it in expanded form, and that pattern will continue forever. So that will be our associated sequence of partial sums. Any questions about that sequence? Okay, what this sequence is trying to do, and it's doing it in stages, is trying to take infinitely many terms and add them up. But notice that every step there is finitely many. So all the terms are well defined. If I have finitely many terms, we can always add these up. But n is going to tend towards infinity, so we're essentially taking the limit of the sum of every single one of the terms in the sequence. And we want to ask the same question: would that limit converge or would it diverge? And that's what we're going to refer to as a series. We can now say the associated series. By associated series, I mean if you give me a sequence, there is a series. I mean, it could converge or diverge, but there will be a series. It is denoted by the summation as I goes from 1. Here we're not going up to n. We want to sum every single term of the sequence, of which there are infinitely many. So we go from I goes from 1 to infinity of a sub n. And we've done it. That's what we mean by a series. Any questions about it so far? Okay, we should pause for a moment because this is getting pretty abstract, I think. Sequences are already interesting. We wrote an associated sequence of partial sums, and we're imagining a series where we sum every single term. But there is a goal to this. It's not just for the sake of it. What we're trying to do is take things like e to the x and do a special series that we'll call power series, as n goes from 1 to infinity, of x to the n divided by n factorial. So we're going to take transcendental functions like e to the x, sine x, cosine x, tangent x, natural log x, and so on, give a power series, and use that to solve interesting antiderivative type problems, which can be leveraged to solve many different applications in differential equations as well. So this is kind of an amazing leap. We take something that's a discrete set of points in the sequence, we're going to somehow connect the dots with a power series, and this is the next step. We have to first have a notion of what is a series in the first place. But questions to that step so far in the definition? Okay, so now the next trouble here is, if you write something like this, it now really means A1 plus A2 plus A3 plus this sum goes forever. There are infinitely many terms we're going to add to at once. So we have to have a notion of when does that converge, when does it diverge? And the sequence of partial sums will be our guide. We'll say that the series converges if and only if the sequence of partial sums, S sub n, converges. But that's great because 11.1 is precisely the question of when does a sequence, any sequence, converge or diverge. So we can say, moreover, if the limit as n goes to infinity of S sub n we're going to say it converges by giving it some value, let's just call it S for total sum. If this is equal to S for sum S, some real number S, then we'll say that the sum, as I goes from 1 to infinity of A sub n, is equal to S, and it converges. So that's the definition of the sequence of partial sums and the notion of when you can actually add all of them together. It just depends on this particular limit. But any questions about that full definition so far? I think it's time to go to Excel, because I think the best thing we should do is, let's pick a particular sequence. We'll look at the sequence of partial sums, and then we'll predict whether or not we have convergence to a particular value S. So the sequence we want to use is the so-called harmonic sequence. So let's say, consider, for the next problem, the harmonic sequence, or series rather, which is the summation as n goes from 1 to infinity of 1 over n. The problem says to determine by plotting the sequence of partial sums if this series converges or diverges. And this is really a lot of work. So we're going to make Microsoft Excel do the work for us. I won't make you folks do this by hand. This is just way too much computation. But if you like, you could go to Excel like we're about to. So let's get a blank worksheet. Any questions first? Okay, the setup on this is we have to take this series that we were given. We need to now go backwards and write down what the actual sequence was. So that would be my first step in analyzing this problem. So we can say the sequence, which is associated to the harmonic series, that's a special series because it has a name, is A sub n, as n goes from 1 to infinity, defined to be just 1 over n, as n goes from 1 to infinity. So it's not a huge leap, but whatever you're given inside the summation symbol is the nth term of the sequence that we want to look at. So let's first plot that nth term. So in Excel, I'll hit the light so we can see the projector. I'll start with, say, an index. And let's say maybe plot, how about 20 terms? That ought to work. So start with 1. Here we can go equals the previous entry plus 1, and that should copy all the way down to 20, like so. So now we have 20 terms. I needed that because that is the input to the sequence. We're thinking of function notation, we write that. So now we can define the formula, and we'll call this the sequence. An equals 1 over n. I don't know how to make a subscript in Excel, so I'll just write an rather than a sub n. What we want to do is go and take each entry and divide it by, or rather take 1 divided by each index, a sub 2. So here, the first term should be 1 divided by 1. If we go down 1, it should be 1 divided by 2, so a half, and then so on forever. But then we can copy paste this all the way down. And you can imagine this is going to be horrible to do by hand, so we'll only do it with Excel. And I won't force you to do this as a homework assignment, but it's worthy for visualization's sake. So there's all of our terms. Let's plot just the associated sequence just to visualize it. So if we take this, and I guess a dot plot should do the job. I think I have a very old version of Excel. This all looks It's insert, thank you. This all looks completely foreign to me. Something there's got to do it. So there's the sequence of 1 over n. So what can you say about this, the convergence or divergence of 1 over n? Yeah, it's converging, and it looks like it's converging towards 0. I mean, look at these decimal places. So we can say so far by what we see in Excel and definitely we could take the limit of 1 over n, that is definitely 0. We can say a sub n converges to 0. Now we want to determine the convergence or divergence of this. But remember, this is equal to 1 plus a half plus a third plus a fourth forever. It's encouraging to know that 1 over n is getting smaller and smaller. It's tending towards 0. So even though we're adding infinitely many terms, those terms are approaching 0 themselves. But still, this could converge or diverge. Knowing this converges to 0 is not enough to resolve what happens to 1 over n. So now we're going to throw in a new column and look at the sequence of partial sums. Any questions first? Yeah.
So on homework, if we know that that diverges, is there any point in doing this to see?
Correct, that's an actual bona fide theorem. It's called the test for divergence, and it says, it's probably the most important test for divergence we have. It reads if a sub n, as n goes from 1 to infinity, diverges, then the series as n goes from 1 to infinity of a sub n diverges.
But if it's opposite, it might not be the same.
Correct. So the problem is, this is a if-then statement, and the logic does not reverse. We would have a contrapositive that says, if this converges, then this converges. So I can reverse the direction and negate both statements. However, if it said, if this diverges, if and only if this diverges, it could go backwards both ways. But sadly, the converse, this diverges, does not necessarily mean the other thing diverges, which is horrible. So we have to be very, very careful with that test for divergence. If we converge to 0, we have found essentially no information, which is horrible. Or we could say a little bit more here. Instead of diverges, let's say if the sequence does not converge to 0. That'd be a little bit better, because if it converges to 1, we'd be adding ones or things close to 1 infinitely many times, and the value of that sum would tend towards infinity. So diverges is okay here, but this is the actual legitimate full theorem. If it does not converge to 0, then the series must diverge. So let's see what happens then with our harmonic series. But first, any questions? Okay, so let's take a look at a new column here where we want the sequence of partial sums. And really, I think the major punchline to a problem like this is a huge definition, and we have to really walk through each part and visualize it to really tell what's going on. And that does take some work, but Excel is here to help. So this is the sequence of partial sums Sn. So to do that, Sn is defined first by taking a sub 1, which is this very first term. So we can say that the first term is just 1 itself, with lots of decimal places. But the next term is going to take a sub 1, notice that is this entry above, and add a sub 2. A sub 2 would be that entry. Does that look correct to folks so far? So that would be a sub 1 plus a sub 2, 1 plus 0.5. That didn't look quite right. Hang on.
It didn't have the first term for some reason.
Oh, it was lying to us. This, maybe I forgot to hit plus or something. This plus this. Okay, that's a little bit better. So we took a sub 1 plus a sub 2. That should be a 1.5 exactly. Then, if we go here, that'd be taking a sub 1 plus a sub 2. We just need to add a sub 3, which is this quantity right there. Oh, don't forget the plus though. So we would go, hang on, this is a little messed up. So I will take this plus that. Does that seem about right to folks? The entry right here where the cursor is A1 plus A2. But I went left one, where the red highlighted is, that would be the A3. So this should be about 1.83 bar. That looks about right. So if we take this and copy the pattern down, it will do this the remaining number of times until we get to 3.5977 and some change. So this here is the result of totaling that entire column of numbers. Do you folks believe that so far? Does that look all right? Okay, so we have the plot of the sequence. We may have to hide that because We don't have very good resolution on this projector, or just shrink it really, really badly. Now let's do the sequence of partial sums. So we'll go to Insert, I think it was here. We should do the same chart. And this is what the sequence of partial sums would look like. It looks like it's growing, but it also looks like it's possibly settling. Would folks agree on it settling on a number? If it settles on a number, what would you say the number is roughly about equal to?
Probably 4.
I would agree with that. It looks like it's tending towards 4, like it's leveling off, and this is as if it's a horizontal asymptote. But remember, these things are extremely deceiving. Let's add some more terms and see if it really settles on 4. If that's the case, if I add, say, a whole lot more terms, we should be able to visually verify that this column, the sequence of partial sums, is getting closer and closer to 4. Does that make sense so far? Okay, so let's add a little extra flair here. Let's go to freeze panes like that, so we can just keep the top row the same. And we're going to take this and copy it to, we don't want to go crazy, let's go to 100. It went up to 5, so it's exceeded 4. That just means maybe we have the wrong graph, right? So let's look at a new graph of the first 100 terms in the sequence of partial sums. So here, all I'm doing is looking at the first 100 terms of the original sequence, add them up, and you get to about 5.1773. And the new chart, I'm not sure how this is going to look. Did it really work? No, that's the wrong one. It's somewhere up here. It looks like,
That's it.
yeah, looks like this. So now it looks like it could still be settling. Would you folks agree? But then again, we could say if it's settling, maybe it's settling at 6. It doesn't seem like our intuition is really working, right? It almost seems like the more we go, the larger this quantity would actually get. But that would mean we have divergence. But let's test it out. Let's take this and go up to, I mean, we can go really crazy here. This is something you cannot really do on homework by hand. So we've added 2,411 terms and we're up to 8. It seems like it's always increasing, but then we might say, well, maybe it's settling at 9. But once again, we could do this forever. And if you read section 11.2, the book is going to prove that the harmonic series in fact diverges, which is really kind of unpredictable, I'd say. So now it's up to 9. And the claim is, if you come up with any number, say 1,000,000, I just need to get to the right level here, and we can exceed 1,000,000 on this series, the harmonic series. But that would mean this is patently diverging. It's not settling at all, which is horrible. The sequence, I mean, all the way at term 5563, is getting pretty close to 0, whereas the sequence of partial sums, when we add up 5,568 terms, is just growing and growing at every single step. So 1 over n is just not shrinking fast enough is the problem with this thing. So let's go back over to our original problem. We can say that the harmonic series, this diverges to infinity. The book gives a really clever proof on that, and we'll prove it in a much easier way in section 11.3 after the exam, using the integral test. There's finitely many terms in this partial sum Sn. So this will carry on all the way up to, we get to a sub n, but that's just the 1 over n minus 1 over n plus 1 that we've written. So that's what S sub n would look like if we expand it out, use the formula for the nth term of the sequence. Any questions to that stage? Okay, then we have immediate cancellations right away. So let's do those cancellations on the next line. S sub n would be, well, there's a negative 1/2 canceling with a positive 1/2. Then negative 1/3 cancels with positive 1/3. And negative 1/4, well, we didn't write it, but that would have been a sub 4, and we would have had a positive 1/4. So there is a cancellation in there. Does that make sense? Similarly, we didn't write a sub n minus 1, but if we did, we would have gotten a negative 1 over n, canceling with a positive 1 over n, because a sub n minus 1 is placing an n minus 1 inside here, so 1 over n minus 1. Then it goes minus, n minus 1 inside here would just be a negative 1 over n. So if we wrote this term, the negative 1 over n and the positive 1 over n would have canceled. So there's a whole bunch of cancellations, except for the very first and the very last term. It's like kind of an algebraic miracle in some way. And that's such a nice cancellation. This actually has a particular name. This is called a telescoping sum, to refer to how the cancellation is going at every single term, leaving just 1 minus 1 over n plus 1. So we have a bona fide and easy to work with formula for S sub n. That means we can come down here and say the limit as n goes to infinity of the partial sum S sub n. Remember, that's just the same as these entries in the right column. That would be the limit as n goes to infinity of 1 minus 1 over n plus 1. But the limit of the constant 1 is just 1 minus, what would be the limit of that thing? Here's 0? Yeah, we really don't have to show steps on those things. If you have a rational function, you can just assert the value of the limit, and that'll always be acceptable. So that it converges to 1. But this means that the sum, as n goes from 1 to infinity, of 1 over n minus 1 over n plus 1 converges. In fact, whenever this converges, it would converge to the limit as n goes to infinity of f sub n, which we have just found to be 1. So that was our core definition of what it even means for a sequence to converge, or excuse me, a series. Always have to keep those two things separate. For a series to converge, the sequence of partial sums, which you have just found to be this, must converge as well. So we can say this is a convergent, or it converges as a series. Any questions with that one? Okay, so this is kind of a weird problem because we had to go strictly to the core definition to determine the convergence or divergence. But what we're going to start to do from here on out in 11.2 and the remainder of the chapter 11 is start to collect tests that look like this. Test for divergence will be, say, the last part of 11.2. We're also going to do a geometric series test for divergence or convergence, which is very similar to what we've done here, producing a new formula. But I think this is possibly a good stopping point. Any questions so far with what we've done? Okay, if you do have questions, feel free to stick around. And the assignment for 11.2 is just going to be kind of another short one that would be due after the exam, since we'll only complete it next week.